guys, today we are going to start the different laws related to the heating. Okay, and so first, whenever we are going for the discussion on heating elements or heats, then we have to recall scientist Joseph Stephenson. Joseph Stephen. Okay, so you can see the image. It is what is shared by
सर
the.
आवाज नहीं आ रहा ठीक से।
आवाज नहीं जा रहा है. ओके.
नहीं सर। सर मतलब बहुत कट कट के आ रहा।
अभी जा रहा है. अभी पहुंच रहा है.
हाँ सर।
Okay, so this is Joseph Stephen. Uh, he was you can say he is the father of heating element, heat laws, heating elements, etc. So he
सर आवाज बहुत कट रहा है सर।
okay, okay, आवाज की कट है. Actually, Joseph Stephen was innovated so many laws on heating elements. Okay, and that's why we can say he is the father of heating elements or heat calculation, heating body design, etc. So first, this is the scientist, and now I am sharing in our topic Stephen's law of heat radiation. Okay, now we can see Stephen's law of heat radiation. You can see this light. Okay, here you can see the Stephen's law of heat radiation. The law is very useful in designing the heating element for the oven and as far as the resistance in concern. So which type of ovens are related? Generally in our mind it is heater, just like a room heater. It is a normal cooking heater, or it is a furnace, laboratory purpose furnace, which is used for melting in some metal, etc. And another heating elements nowadays it is coming. This is induction heater. So in this type of heater, in this type of heating where the radiation etc. are related, there the Stephen's law is very useful. So we have to know this, and you know that in utilization somehow we have to make some metal, we have to design some metallic body. Then we have to use the various heating element and heat application. Just like you can say the welding, where welding is done, there also the heating is there. And in old version, there is a gas welding, arc welding, we can say hermit welding for railway purpose. Hermit welding is used for railway purpose, railway tracking. Nowadays, we are using the induction heating for welding purpose. Okay, and induction heating for any melting a metal. So at that case, we always follow the Stephen's law of heat radiation, and we have to design such a heating body so that it can be very much useful, efficient, and economic for our utilization purpose. So let's know what is the Stephen's law and then its application, and then we will go for a designing purpose and problem. Now, the statement you can see here is the statement is here, and the amount of heat radiation from the source to the target object is mainly depends on the temperature difference between the two. So, what is it is saying? The meaning is that we we just realize that the temperature difference between the two means if we are using two objects such one is source and another is sink. May, uh, Source is radiating its heat and the sink or the another object it is consuming heat from the source. So the radiation from the source to the target object is mainly depends on the temperature difference. So if there is a 100-degree temperature for the source and 10-degree temperature for the sink, then the radiation is depending on the 90 degree because 90 degrees difference. But if there is a 100-degree temperature for the source and 90-degree temperature for the sink, then the temp and the radiation is depends on the 10-degree temperature. So this is the main topic. But depending on this topic, we can use the radiation and the you can see there is a radiation heat formula. What is the heat radiation? It is given by the Stephens, scientist Stephen, that is 5.72 into 10 to the power 4. This is the Stephens constant. Then K into E, uh, here you can see, okay, I am sharing another slide because this is not shown properly. Okay, here it is total. Just one minute. You can see here. If you can see, okay, the formula is not shown properly because some portion is cut it. Okay, okay, now it is coming. No, it is not coming again. Okay, so you can see the 5.72 into 10 to the power 12, 10 to the power 4. This is a Stephen constant, then a constant K, and this is a E. E is a radiation body, and this is T1 is the temperature, by 1000 to the power 4 minus T2 by 1000 to the power 4. So T1 is the heating element 1. You can say this is the source, and T2 the object or the you may say sink. This is the T2, the temperature. Now the unit is watt per meter square. Okay, so heat radiation H is 5.72 into KE A into 10 to the this is in the brackets into in first bracket T1 by 100 to the power 4 minus T2 by 100 to the power 4 into this is the unit is watt per meter square. Now in previous equation we have written and this is 1000 but here it is 100. Why? Because 10 to the multiply 5.72 to the power 4, so this 10 to the power 4 is nullified the 10, so it became 100. Okay, this is the final this is the final equation for the Stephen equation. So you can see the heat radiation it depends on these are the constant. So only variable is the T1 by 100 into 4 and minus T2 by 100 into 10 to the 4. Here is also 4. So this difference is proportional to the heat. So here we can say the energy is proportional. Heat means in energy. E is proportional to T to the power 4, where T to the power 4 is the temperature and, and energy is the E. So this is the main vital formula. So energy is proportional, maybe radiate, maybe consume, whatever may be. It is depends on the temperature to the power 4. If temperature is increased by to the power 4, then energy will change. Okay, yeah, you can say if 1 unit of energy will be changed, then temperature will be changed T to the power 4 unit. Okay, so we can say E is sigma into T. Sigma is a constant, temperature constant. So this is sigma equal to E by T. Okay, this is our working formula. Actually, main working formula is this is H. Whenever we are going for the numerical application, then you can see what is the application. Now we should discuss on the requirement of good and good heating elements. You can say healthy heating elements, anything, or economic heating elements. And so, what are the requirements for good heating elements? Now, first point, it should have the high resistivity. First point, it should have the high resistivity so that the small length of wire is required to produce a given amount of heat. Okay, so what does it mean? It means if you are using if you are using, say, this is copper wire, you are using the silver wire, or if you are using the gold wire, then it's heating. It doesn't produce much heat to respect to the nichrome wire. Okay, yeah, your filament. Okay, so but if you are use your nichromine just like your heater, then a small amount of current will flow and it will produce so many heat. But if you use copper oil, if you use gold oil, if you use silver oil, then it doesn't produce that much amount of heat. So the resistivity, you have to choose the resistivity, it high resistivity of the element. So a small amount of oil may produce high amount of heat. Okay, you have seen the nichrome wire. Nichrome wire is the one of the best element, one of the best, not least. This is used for your heater purpose. This is used for your furnace purpose. Some furnace you have seen where gold are melted, where a small amount of metal are made in laboratory purpose or some small purpose. There some furnace are used where this electric heater is used. Okay, here is square type of furnace where the all this surface is inner surface are covered with uh, the nichrome wire, and then it's produced so many heat, and the gold or metal are put into a crucible till under this furnace, and after some time, after a specific time, with using some flux we can melt this type of metal, and then we can use, but it is required for the small amount, not the high amount. Okay. The next point is it should have the high melting point. So you are using in soldering wire. If you are using soldering wire, then small amount of heat may melt this body, but it should have the high melting point. So it became it, you can use this metal in high temperature. Okay, so you can see this. Okay. Next, the third point is it should not oxidized at the high temperature. So whenever we are using for our burner purpose, for our oven purpose, you have seen so many parts of the oven, of the gas oven, became destroyed or became damaged after a few months. But only the burner, where is made by the brass, it is not damaged or became rusted. Why? Because these metal are used capable of enduring in high amount of temperature. But the surrounding element, maybe iron case and the plates of the steel which is used in your gas oven, then it is not highly temperature nature enduring body. This is the it maybe became oxidized iron. It became oxidized after few days. So we have to change the oven parts. So we should use the this temperature durable metal which is not oxidized at the high temperature. Okay, so somewhere this is the alnico, somewhere it is used, and this type of metal, steel, in this type of metal is not oxidized at the high temperature. Okay, high grade steel, not low grade steel. Okay, so then this is coming for the point number 4. It should have the higher specific resistance so that the overall length may be smaller to produce a certain amount of heat. Same point, just like a high resistivity and specific resistance. Okay, and then we are going for the point number 5. It should have the low temperature uh, coefficient, so that the resistance remain in appreciably constant even while increase of the temperature required for the automatic temperature. So the low temperature coefficient means it is not hampered with the temperature changing. Okay, it is not efficient, it will be the coefficient. So if we use so many type changing of temperature, say you are using 100 degree temperature, after few minutes you are using 1000 degree centigrade, and after few minutes you are coming in in 900 degree centigrade, after few minutes you are using 2000 200 degree centigrade. So abruptly you are using in the temperature at that body, at that point, and if low temperature coefficient is there, means temperature changing is not doesn't matter in change of its radiation, of its oxidation, etc. So this type of materials are so much required. Okay. Now we are coming. It should be non-corrosive. Okay, it should be non-corrosive. If you are using such a halogen body, if you are using some radioactive body, then it will may fulfill your desire, but it will become a noise. It will become some hazardous area. Uh, It may destroy your human life. So it should not be required. Now, 7 point, it should be economical. This is the main target of our all engineers or professionals, because if some things are much highly expensive, then we can use it. It became restricted, but if it became the economical, then we can apply these things to so many areas. Say we are using our batch production, we are using some other furnace, just like a arc furnace. This is also a electric driven furnace. Yes, you have certainly you have seen arc furnace or heard about this. A normal coke oven furnace, normal gas furnace, but we can't compare with our electrical furnace with this, because this, this type of cost is very minimal, nominal. But if we use the radiation type, heater type furnace, then the cost is much high, right, respective to this point. So as this is not much economical than this item, then you can use for the industrial purpose. But nowadays induction heating coming to the in the market, and it is used for the boiler, it is used for the small purpose, say welding. So we can use this type of things. And in previous cases, gas oven, uh, arc welding and your arc welding and your gas welding was became costlier than your induction and welding, induction heater type welding. Okay, so this is the, because this is the economical. That's why we are introducing this, this induction heat, induction type welding. Okay. Then the next point is designing of heating element. Okay, now circular type heating element. Say we or you want to design a heater which is used for your local purpose. You can purchase now for your small laboratory purpose, small industrial application purpose. You can produce. You can use uh, you can't use the high element, high expensive element. You have to design your specific work done, and you have to design some specific heater. So then you have to apply these concepts. Look, how could you select? How could you to estimate a heating element for your purpose? Now, this is, we can say, this is V is the supply voltage, R is the resistance, and E is the resistivity. Okay, E is the resistivity. This is the ohm meter. Their meter is not showing, but it is ohm meter, ohm dot meter. Okay, just remember, guys, you may note down this. So we can say this is R equal to resistance equal to rho into L by A. Okay, this formula is known to all. This is coming from our scientist Ohm and Ohm formula of Ohm's law, and this is R equal to rho into L by A. So this is a formula, uh, and we can say P equal to V square by R. How it is coming? We know P equal to V into Y cos phi. Now, if cos phi were, we are assuming that cos phi is uh, unity. So it became P equal to V into I. We know I equal to V by R. So V by R into V. So it became V square by R. Okay. I just recall you because these things with the electrical engineers maybe thousand times here are doing this. Okay. So now it is coming P equal to V square by this formula R is replaced by this point rho into L by A. Okay, you know what is the length, A is the area, cross section area, etc. etc. Okay. So, hello, hello. Okay, and now you can see this is the D, this is the diameter, and this is the, say this is the round shape wire, and we know pi r, this is 2 pi r. Okay, this is equal to 2 pi r. And surface area is 2 pi r l. Here is L. And look, you can see this, we can say this is the pi, this is 2 pi r l. We can write pi d r because 2 r is the d diameter. Okay, so 2 pi r, 2r became the d, so we can write pi dr, and a is the area is the pi d square by 4, pi d square by 4. Okay, so this is the, this is this is the our formula, and we can put it, just we can put it, p is the v square by rho into l by this pi d square by 4, and we can see this is the v square by pi, this pi d square coming to the upper side, and this is a 4 pi 4 rho l, and ultimately we are getting p equal to v square by pi, sorry, v square into pi by 4 into rho into d square by l. This is d square by l. This d square by l, it is coming separately, but it is a multiplication form. So L by d square is we can say L by d square is uh, v square by v square into pi by this portion, and P means power into 4 into rho. This is our neat equation 1. Okay, now we know this formula. This is heating in radiated heat or heat dissipation by the Joseph Stephen, scientist Joseph Stephen, and H is a 5.72 into 10 to the power 4 into K is the constant, is the resistivity. Here is the T1 by 1000 to the power 4, T2 by 1000 to the power 4 watt per meter square. Now, the total heat dissipation H into surface area, H into the surface area. Okay, the total wear. So you are designing a coil, a nichrome coil for your heater. So total surface area is required. So heat H into surface area is the total heat dissipation. Okay, heat is here. Now under the thermal equilibrium, the input power is the P, whatever we are given, and H into surface area. Into this is the pi dl, because we have seen here pi dl, okay, and h surface area pi dl into h. So we can write d by l square. Here we get uh, d, here is l by d square. D by l square will be written. So d square by l over. So 4 rho into h by r square to the power 2. So this is the main formula, and we don't go for the further. We are just going for the, because it is up to this we are fulfill our problem. And look, this is the main topic. P means power. Required power is H into H means heat. How many heat you are required? Say you want to melt you want to melt some copper or some metal body, that is where a small metal body, where you have to require 200 degrees centigrade. So the metal body is 0, and your source should be the 200 degrees centigrade. Then it will be melt, and so from here you can calculate. You can this, because these are the constant. These are the constant. So you have to put 200, you have to put 0 over here. You have 1 degree temperature, your room temperature, your atmospheric temperature. This is, or it is called the ambient temperature. Okay, so it is maybe 20 degrees centigrade. So you have to calculate the age. Then whenever you put some age, and you need some power, if you put some power, or maybe you have some heater, you have some heater. So whenever you have some heater, you can calculate it the d, and whenever you calculate d and the length, or the arc and the length, then you can calculate the surface area of the heater element, heater coil element. Then you can easily calculate how much power you are required. Or say you have some only specific power, somewhere you are getting some specific power, and you need some heating, this much of heating. Then you can calculate how long, or how much quantity of your nitromire, or how much quantity of uh, your heating element is required. So this is the main topic for your utilization, and where the welding or heating elements are required in a or particular position. Now we are going for. Oh guys, I think you can understand this discussion. Okay, if you have any problem, you may message me or call me. Sorry, message me, or you may talk. Now we are going for a problem. Look, here is a problem. Look, uh, Okay, it is not showing. I am showing another. This problem is another way. Uh, Look, here is the problem. Uh, you can you can take 5 minutes. Uh, Within 5 minutes, you can solve this because previous discussion was just based on this. If you carefully listen it, you can easily design this element and you can solve this. So guys, within 5 minutes, you can complete and then I will discuss everything. Okay. Now problem is here a 40 kilowatt a 40 kilowatt single phase 220 volt circulating wire is used. So here you can get your power. P is given. Now we know rho is the 1.09 into 10 to the power 6 minus 6 R ohm meter. Here is the ohm meter. If the wire temperature, if the wire temperature not to exceed 1127 degrees centigrade, now temperature in the pot is 4 to 7 degrees centigrade. Assume E is the 0.9, what is the emissivity, K is the zero point 0.6 radiation emissivity. What would be the temperature of the wire when change it to the cooled? Means now you can see from this your power is fixed, which is given by 40 kilowatt. Okay, 40 kilowatt power you are putting, and your temperature is 1127 degree temperature is at this point, and the temperature of the pot is 427 degrees centigrade. And so you have to reach this amount of centigrade because it is a required, and after reaching it is coming through the cool down, and this is the when it is cooled down means this amount of heat is exchanged. Okay, so this to this, what temperature is here, and this is the highest temperature. So this temperature is T1, this temperature is T2. So from T1 to T2, when temperature is totally transferred, then after then it became cool down. Okay, so if you say after cool down, how many temperature were transferred? Because one, 127 degree centigrade minus 427 degree centigrade, and then this amount of temperature was exchanged. Okay, so what would be the temperature of the wire when it will be the cold? Okay, so you have to estimate it. Now T1 is the 1127 degree centigrade, and this centigrade to the kilocalorie. Okay, calorie. Then 2 or the Kelvin scale. 1127 plus 273. This is 1400 Kelvin. And same way we have to add 270 with this body. So T2 is the 427 plus 273 is the 700 Kelvin. This is the T1 and T2. We know H equal to means heat. It is a transferred heat uh, or the radiative heat. This is 5.72 into 9. This is a K. And look, whenever you don't use 10 to the power 4, then you have to put 100. But if you use 10 to the power 4 here, then you have to put another 0 over here, then it will be the 1000. In previous discussion you have seen. So this is the k and this is the e. These are the constant. Now we can find out this amount of heat. This amount of heat was as radiated. Okay, so from this heat we can we can evaluate the resistance of the element. R is the V square by P. So this is a 220 by 40 into 10. Okay, V square into 10. And now, and this is a 10. P is a watt. What are the kilowatt? 20 kilowatt means 40 into 10 to the power 3. Here 10 to the power 3 is not shown here, because some photography cutting. So its became resistance should be the 1 to 10 ohm. Here some dot is coming. So resistance is 1.210 ohm. Resistance is 1.210 ohm. So R is the rho into L by A. So 1.210 is equal to rho into L by A. We know rho equal to 1.09 into 10 to the power 6 into L. A is the pi R square. Okay, and then we are getting from this formula 1.09 into 10 to the power minus 6 by pi. So rho by r square it is separated, and it is coming L by r square, it is coming this amount. Okay, now we are just putting here 1 means equation 1. R L by r square is the 3.486 into 10 to the power 6. This is the equation 1. Now we are coming thermal equilibrium. Say this is the thermal equilibrium means the source and sink all are became same position. No heater exchange. At this point, P equal to input power. So we are doing thermal equilibrium means the temperature dissipation becomes stop here, because if we at that point we don't reach, then this heat is changing. We are collecting the fixed body. This is the heat. Whenever this heat became fixed, whenever thermal equilibrium occurred, each H equal to surface area H into surface area P, how much input power you have given. This is heat into surface area, relative heat into surface area. This is H into 2 pi RL. So we can say this amount of input power we have put 40 into 10 to the power 3, because this is a kilowatt and this became the watt. So this became, what are the heat? This is 111243. This is heat, and then we are putting into 2 into 3.14. Okay, and then R into L. Okay, so RL is the, so from this point we can calculate R into L is because this divided by this portion, then is this became R into L equal to 0.057. In equation 1, this is R into L we have solved, but we know what amount of R was coming. R was 1.210 ohm. So from here we can put equation 1 and 2. We can put L equal to 3.4. Look here, you have just calculate this equation 1, R by L square, and here R by L square equal to 3.486 into 2 by 6, and this R square is here. Okay, and then R into L, because we have to perform this R into L is the 3 point this portion, and another R to the power R cube, because we are multiplying R. So now in this way we can put this RL, this value of RL and this. Okay, so this is 0.057 into R cube. So R cube is this point. R equal to, so R equal to 2.53 millimeter. Okay, this r is this r is radius, not resistance. Okay, here in previous question we have calculated the resistance. This is also r, but this is the capital R. It was how much? It was 1 point where we have to calculate 1.210. This is the r means resistance, and here smaller means the diameter. Okay, and from this area we can find out L. L is also putting this element because from this here RL is 2.31 meter. Okay, these are our calculation. So from in this way we can calculate the nichrome wire or the heater length and your radius. Okay, and if you got the radius, then you can easily find out the diameter. So the problem is coming in this way. Some power is given, you have to calculate the heater surface area, heater length, or heater resistance, heater diameter. And sometimes this data was given, heater specification was given, then you have to calculate the required power. So this is the our main motto. Whenever you are going to your practical life, then so many times you have to estimate some things. How many power required? How many heating elements are required? How many times it will required? So this is the main utilization application for your heating radiation heat. Because if you know the radiative heat, then you can easily apply, calculate, or solve many problems. Okay, so this is our new laws on design of heat element uh, and some Stephen's law. And so, guys, you can understand this. And now I just stop here.